This is lecture 30. So in this we continue the discussion about examples of morphisms and fibers of that to come to the as a starting point for the next question to next topic to understand. Okay, so back similar example, because I want projection to the x-axis. Let me orient the picture this way, the arrows this way. Okay, so this is the picture, and the variety of this would be so every function, every point where either x vanishes or y vanishes, which is just the union of the axes, and here is just the line x. Okay, so now let's take some alpha here. So we get x minus alpha here. Okay, so here we would just get x minus alpha. Okay, so let's work that out. So x minus alpha and then xy. This is the ideal inside kxy that we need to worry about. Okay, but this is the same as x minus alpha and alpha times y, because we are just substituting x minus alpha, x as alpha. Just one observation: if alpha is 0, it is subsumed in this case, but let's just make sure that we understand. If alpha is non-zero, then it is fine. Even if alpha is 0, so if alpha is 0, then we just get x here and then 0 here, but that is okay. X comma xy is same as this. Okay. Once x is there, one does not need this. Okay. So even if x is 0, then it is still fine. Okay. So this is the thing. However, the behavior is quite different in the two cases. Where alpha is x is alpha and y, the value of depending on alpha is 0 and alpha is non-zero, what the fiber is very different. Okay, so let's work this both out. Let's just work for alpha equals 1 and alpha equals 0. Okay, the fiber is kxy mod x minus 1 comma y. Okay, so this corresponds to the point 1 comma 0. Okay, because if alpha is non-zero, although in both cases the description of the ideal is as a formal thing, it is correct. There is nothing wrong. But what this ideal is depends on what that alpha is. If alpha, this is alpha not equal to 0. Let's just take alpha to be 1. Okay. If we take alpha, or we could just take alpha here itself. The ideal generated by alpha y and y are the same. So you can just take. If alpha is 0, then we would just get k xy modulo just x, but this is the y-axis, right? Every point on the y-axis satisfies this equation. So, which is what the fiber over some point alpha here is alpha comma 0. That's what goes to this point. However, to the point 0 here, the entire y-axis maps, and that's the. Okay. So there is a difference in earlier case. All the maps were finite. I mean, the fibers were finite, but here that's not the case. Although, if you look at it, in some sense, there is not much difference. Which is, we have a polynomial ring in two variables. We went modulo one equation, and then we are just looking at the map from one of those variables to this. Okay, so in that sense there is not much difference between this and the previous problem. Okay, but there is, okay, which is what we just saw. Okay, so now let's look at another. Let's modify this with a slightly different fashion. So now we consider a different variable t, and here is just kxy mod xy, and this map, okay, which is now t goes to x plus y. So in other words, when we say t to alpha, t to some value alpha, we are setting x plus y to some value alpha. Okay. So that would be an entire line. Some line. I mean, if you draw it in a real picture, it will be some line with a. So this is the x comma xy gives that. T is just this line. Okay. And if you take some alpha here, it is not just the point. T is not same as x. Okay. T corresponds to some line here, which, so let's do that. So some alpha here. So here is t minus alpha. Okay. Here it means kxy modulo t minus alpha. Sorry, t is just x plus y minus alpha and then xy. Okay. Now, irrespective of the value of alpha, this has one or two solutions. Okay. Okay, so let's do that. So, so if alpha is not equal to 0, okay, the equations x plus y minus alpha equals 0, xy equals 0 has two solutions. You can work that out. And if alpha is 0, we get kxy mod x plus y comma xy, okay, which is really, if both these functions vanish, it can only vanish at the origin. Right? X and y have to vanish. So either x is 0 or y is 0. But as soon as x is 0, this forces y also to be 0. So this is, okay, has only, so the max spec of this corresponds to one point, which is just the origin. But as we saw earlier, it has some additional structure to it, not just one point. But whatever it is, when we go back to this picture, the fiber over alpha is this, not a point, but it's a line like this, x plus y equals alpha. Okay. So it intersects the given variety only in finitely many points. So the fiber of this map has, the fibers of this map are finite, while in the previous example, there are fibers which are not finite. Okay. So we will come back, revisit this point after we discuss a few, we prove some results. I mean, we set this up and prove some results. Okay. So it is in general true, it is true that if R is a polynomial, we'll prove this in the next lecture or the one after that, a polynomial ring in a polynomial ring over a field, is a finite type algebra, meaning finitely generated algebra over a field, then there exists a polynomial ring A such that, okay, the fibers of this map let's say algebraically closed field for this, okay, spec R, polynomial ring A such that with a morphism A to R, algebra over a field and a morphism A to R such that the fibers of this map fibers are finite. Okay, so that's the picture that we had here. So here is some finitely generated algebra R there is a polynomial ring A with this as finite. Okay. So this is in general true. It's okay. But it is not always true that okay, one could have sort of bizarre behavior about fibers, but here we somehow find nice fibers. So we need to develop enough to understand and prove this theorem. Okay, we'll prove something stronger than this, and so this is what we want. Okay. Okay. So now we start a section called integral extensions, integral elements, integral extensions. So, so given a map R to S, so this is what, okay, so let R to S be a ring map. Okay. We say that, so let S be inside S, element of S. Say that S is integral over R such that if there exists a monic polynomial in Rx, okay, that that S satisfies. Sorry, I should just say if let me just rewrite this. If S satisfies a monic polynomial in Rx. Okay. So just so what does that say? It says that so there exists there exists some R1 through Rn in R such that when we substitute xn plus R1 xn minus 1 plus and so on Rn, when you substitute S for this one, we get 0. Okay. So just one point, when we say R1, so when we say, so here we have to evaluate things of the form Ri times S to the I, S to the n minus I. This, remember, is just phi of Ri times Sn, S to the n minus I. So whenever we are not saying this, so this is phi, we are not saying this is injective, and whenever we multiply two elements inside here, the action is always through this ring homomorphism. I mean, that is a standard thing. We often don't write this, we just say Ri times S to the n minus I. That's what this means. Okay. Say that S is integral over R if S inside S is integral over R for every S inside S. Okay. So let's look at some examples. Okay. First one, suppose K is a field and F an algebraic extension of K, then F is, every element of F is integral over K. this is nothing different from just algebraic. In this situation, integral means algebraic. There is nothing different. Okay. Example 2. We could just think of this in a formal setup, that we could just join a variable x and then just kill a polynomial like this, and the new ring will, the image of x will automatically be integral. Okay. So if you take R to Rx modulo Px, where Px is monic, okay, then the image of x in Rx mod Px, the residue class, is integral over R. Okay. That is the another example. It's sort of formally constructed, but okay. 3. Another ring that we have seen and we have become familiar with is this k t squared t cube. Okay. And okay, so inside this, look at the subring k t squared. Okay. Now t cube, so this is the s that we are looking at. T cube satisfies t cube square, so t cube satisfies x squared minus t squared cube. T squared comes from the subring R. Okay. This is from R, this is t cube is from S. So t cube is integral over kt squared. Okay, in that ring. Okay. And finally, a non-example. Okay, so this is an exercise. If you take z and you take invert something, let's say we just invert 2, z adjoint half. So this is localizing. Okay. Inverting powers of 2 is is not integral over over z. Okay, that is, if you try to write half has to satisfy an integral equation, we will fail. Okay, so do this as an exercise. So it's not integral over s. Okay, so we would like to understand integral extensions. So definition. R to S ring map. Say that this map is a finite map or S is a finite R algebra if S is a finitely generated R module through this map. Through this map. Okay, so the terminology is a little confusing. We talk about finite R algebras and finite type R algebras. Finite type is as an algebra it is finitely generated. Finite is as a module it is finitely generated. Okay, so and any algebra has a module structure through this map. So okay, so now here is a proposition. Okay. Let phi from R to B to S be a ring map, S inside S, then the following are equivalent. 1. S is integral over R. 2. The subring which is generated by the image of R inside S and little s of S is, the subring is finite over R. And 3, there exists an R subalgebra S prime of S. So it is a subset and it is a subring, but the map from R to S goes through this S prime. So it contains the image of phi. So it is, that's what we mean by subalgebra, such that S prime is finite, is a finite R algebra. Okay, so let's just revisit. So phi is a map and we take an element. First statement, that element is integral over R. The second statement is this is an example of a subalgebra. Okay, so it is a subring of S containing the image of phi and some other things. Okay, so phi of R, this subring is finite over R, and then says, oh sorry, such that S is a I think one more statement, and little s is inside S prime. Okay, that S prime is contained inside some finite subalgebra, not necessarily just that. Okay, so that those three statements, and the claim is that these two things are equivalent to S being integral. Proof. One implies two. Okay. So if you consider the elements, so let R1 through Rn be in R be such that S to the n plus R summation Ri S to the n minus I goes from 0, I goes from 1 to n is 0, because it's a monic polynomial. Okay. This implies now that phi R adjoint S is generated as an R module by, so think of it as a polynomial ring. If you have a polynomial ring, let's say kx, it is generated as a module by the powers of the variable. So here it will be generated by 1, s square and so on, but as soon as we see an s to the n, we can use this expression to bring that degree down. Okay, so this is generated by up to Sn minus 1. So let me just repeat this. As it's written here, so this just says how the Ri act. So for now we can ignore this. When we adjoin an element like this, we have to worry about all its powers, 1 s square and so on. But so it will be a polynomial expression in the s. S will be like a variable. I mean, it will be a polynomial in which s takes the value of that variable. Variable takes the value of s, and coefficients are from this ring. So that's what we are considering. But as soon as we see an s to the n, we can use this expression to bring the degree down using elements of R. Okay? So this is generated by this. So it is finitely generated. So it is finitely generated module. So remember, this finite algebra means finitely generated module. Okay, so it is. 2 implies 3 is immediate, because here it says one specific subalgebra is finite. Here it's just asserting some subalgebra is finite. So 2 implies 3 is immediate. And okay, so take S prime to be phi r adjoint S. Okay. So take. And 3 implies 1. Okay. So we'll use a determinant trick. Okay. So let f from S prime to S prime be the R linear map given by multiplication by S. So 1 goes to S, and then that's not, we have to specify it for every element of S prime, but multiplication by S. So this is a finite module. Okay. So we can apply the determinant trick. Which we learned a few lectures ago. So what do we need? We need f of this to be inside some ideal times this, and then there's some statement. But here we can take ideal to be R itself. Okay. So what does the determinant trick give? There exists an n such that n depends on the number of generators for S prime. There exists an n such that so there exists R1 through Rn inside R. So if it were inside some ideal, we would get some extra conditions on these things. But here we are just taking the unit ideal, such that Fn plus summation Ri Fi, or maybe n minus I goes from 1 to n is 0 as a map. Okay, as an R linear map. Okay. But apply this to 1 of R. Okay. So f of 1, this is just 1. F of 1 is S. Okay. F squared of 1 is f of 1. Square means composite. Okay. So this is f of S. And f involves multiplication by S, so it is S squared. Okay, and so on. So f to the I of S of 1 is just S to the I, and now apply this whole function to S, and then we would just get, therefore, Sn plus summation Ri Si is 0. S not S to the n minus is 0. Okay. This is the okay. So we will stop this lecture here. Next is again a property about transitive nature of integral extensions and finite extensions. So we will prove that proposition in the next lecture, and then we will then discuss what is called Noether normalization lemma, and then we will get, we will first use the Noether normalization lemma to prove the version of Nullstellensatz that we are interested in. After that, we will prove the Noether normalization lemma, not just in one lecture, but in the next few lectures.